Okay, so today we will finish up talking about conservation of energy and look at simple machines, and then it's just going to be a matter of you guys practicing outside of class, doing as many problems as you can do, and let me know what questions you have. As always, my pattern for trying to help you understand it is to start to make sure the concept makes sense, then to look at how the equations relate to that concept, and then we get mathematical. So today's our day to get a little more mathematical. So let's try one let's start to introduce some math into this process of conservation of energy. Again, this would have been a graded in-class exercise. We could still potentially do some graded in-class exercises. I would just have to have you submit them some other way. And I'm still thinking about how to do that. So hopefully the last month of class here, I'll figure out a way to have us do that. But for right now, let's just go ahead and do this together. You can do it, individually, or if you are studying with a friend, watching this video with a friend in the class, you can pause it and work on it and then check your answer. But this one says you have a 300-kilogram roller coaster. It starts from rest. When the spring is released, the roller coaster goes into a loop-the-loop whose radius is 14.4 meters. Okay, determine the distance the spring, which has a K value of 50,000 newtons per meter, determine the distance the spring must be compressed so that the roller coaster is moving at 12 meters per second at the top of the loop-the-loop. Okay, we're to ignore friction and air resistance. All right, so again, just to make sure this is clear, this spring right here is compressed. The roller coaster is released. It goes through the loop upside down and comes down. We're interested in when it's upside down, moving this way, and we want it moving at a speed of 12 meters per second. So assuming the roller coaster has a mass of 300 kilograms and the people in it, K is 50,000 newtons per meter. It has a radius of 14.4 meters, and we want it moving at 12 meters per second at the top. So go ahead and pause your video when you're ready and work this out. I've provided the bar graphs here for you to help guide your thinking. And then you want to write come up with your energy equation and write it and solve for the distance x that the spring needs to be compressed. So pause the video and give it a try. Okay, so hopefully you've got some bar graphs now that look something like this. Hopefully that was the first thing you did, was think about where the energy is. Of course, at the beginning, the roller coaster is not moving. It's down. If you choose this at the zero height, which is what I did, you have no gravitational energy. There's no friction, so there's no heat at the beginning at the problem, especially, and there's actually going to be none generated at the end either. There's no forces coming from outside our system, so no work being done. So all the energy initially is elastic potential energy. All right. When the roller coaster comes into the loop and goes upside down to this point, it's still moving at the top. So we know there's going to be some kinetic energy, and we know that it's now off the ground. How far off the ground? Well, if the radius is 14.4, then it's a distance of 28.8 meters above our y equals 0 level. Okay, so the y height up here would be the 28.8. Okay, so we should have a bar there as well, and it should be a positive bar. So again, if you don't have the exact same height bars as I do, that's fine, but you really should have a position 1 bar graph that has a single bar where the elastic energy is, and a position 2 graph that has a kinetic energy and gravitational energy bar. Okay, at that point then what we would do is construct our energy equation. So this is the beginning. The initial energy is all in the spring, and then at the end of the problem we have some kinetic and we have some gravitational. Okay, so we end up constructing our equation just using those little equations for the different types of energy. Again, we see that M does not cancel here. That is important, because that means that this would not be a good amusement park ride. Okay, so any kind of roller coasters that launch you at the start are not using a spring, because that would not cancel out the mass. So finishing it up, we plug in our known quantities as shown in the handwriting down there. And if you do everything right in the proper units and you're careful with your math, you should get an answer of about 2.06 meters that we have to compress that spring, which is a very stiff spring, 50,000 newtons per meter, and we'd have to compress it 2.06 meters. Notice that the units do all work out, by the way, if you're anybody that's wondering how the units in this all work out. Energy units, these are all energy terms, but when we go out and solve out for our X, it does turn out to be in meters, and you know, there you go. Okay, so here what we see out in the great American West, we see the mountains here, and we have this skateboarder physics dude. And I've got a skateboarding track here constructed for him. And we're going to set him up in there and let him skateboard on this track. Notice I do have the friction set at none, and I have his mass set to small. And we're going to make a bar graph here. I'm going to click on the bar graph so that we get a graph of the total energy of the skater, okay, or in the system. That should be the total energy in our system here. Any thermal energy generated, his potential energy gravity in the system, and the kinetic energy in the system. So if I set the skater up here and I release him from up in, let's say about in here, you'll notice when I release him, he has a lot of potential energy there, right? And the total energy is equal to his potential energy at this point. Now when I release him and let him skate and press play, we notice that he skates on the skateboard path that I've created for him. And you'll notice that the kinetic energy and the potential energy are changing, but the total amount of energy in the system is remaining the same because energy can't be created and it cannot be destroyed. If I slow this down a little bit, okay, we can follow through and see what's happening. As he comes to the bottom of the hill, all of his energy goes to kinetic, and then as he comes up this hill, he has potential energy, comes back down, kinetic. As he goes over the top of this next hill, he has a good bit of potential, but some kinetic, gains some more kinetic, and then up here, it's all potential again. And of course, without any friction, this will just continue to cycle and cycle and cycle. If I go back to normal speed, it looks like that. You might wonder what it would look like if I increased his mass. Well, increasing the mass of the boy just increases the energy in the system. Okay, a larger boy skating here would have to have more mass, which means he's going to have more kinetic energy at those speeds and more gravitational energy. So we just see the energy of the system go up. But otherwise, the mass doesn't really affect the motion, okay, or even his speed for that matter. If I turn on the friction here, you'll notice that what happens is the friction starts to take the energy and converts it into heat. And in this case, since he stopped over in this bottom part, all of the energy ends up generated and turned into heat. On the other hand, if I were to release him up in here, okay, we know some of the energy in the system is gravitational because he's not down at the zero level. The default y equals 0 level is down here at the bottom of the lowest hill there. And so at the end of this, we find out that the total energy still remains the same, but instead of it all ending up thermal, there's still some here where the skater is. Okay, so hopefully that makes sense. Again, maybe I should turn the speed setting on. So again, if I go back to no friction and release him, once again you can see that the speed dial stays the same, okay, regardless of whether I increase his mass or not. There's really no difference in the speed of the skater. It fluctuates between the same amounts. Okay, all that happens is the energy in the system has to be larger if I increase his mass. All right, but again, with the friction turned on, we lose speed, we lose kinetic energy. Where does the kinetic energy go? It turns into heat. Okay, so hopefully this little demo, this little animation helps continue to reinforce this idea of conservation of energy. Okay, so let's try another mathematical problem right out of your book. It says in the figure we see here, a child of mass m is released from rest at the top of a water slide at a height h equal to 8.5 meters above the bottom of the slide. Assuming that the slide is frictionless because of the water on it, find the child's speed at the bottom of the slide. So again, using our system here, I mentioned in our Zoom lecture, and hopefully many of you attended that you could, if you wanted, once you get good with this process, the bar graphs are not really totally necessary. You could go to a checkbox type system where you have some initial kinetic energy perhaps, and then you maybe have some initial gravitational energy, and then maybe you have some initial spring energy or elastic energy, plus any potential heat generated or that's added to the system actually. On the input side of the equation, it would be heat generated. Here we have no friction, and so there's going to be no heat in this particular problem, but we could use a Q initial for heat, and then plus or minus any work done. Okay, whoops, I put a checkbox there. Okay. And then you would have a system of checkboxes like this for your final, over on your other side of your equation, you'd have a series of checkboxes for where the energy could be at the end of the problem. So starting at the top here, when the child's at the top, we're releasing them from rest. So obviously there would be no kinetic energy. She's being released from rest above the bottom of the slide. If we call the bottom height here 0, then of course there would be some gravitational energy. So we'll put a check there. There's no spring, so there's no spring energy. There's no friction. There's no propane torches or heaters adding heat to the system in the problem, and we have no forces coming from outside our system. So all the energy is initially gravitational energy. At the end of the problem, so now if we go back and rethink the problem, from the end of the problem's point of view, at the bottom of the slide, she'll be down here, and so she'll have no gravitational energy, but she will be moving, we suspect. Right? Again, still no springs, still no heat generated because it's frictionless, still no work coming from outside. Okay, so if we use a checkbox system, it looks like gravitational energy is going to be converted to kinetic energy. Okay, again, the traditional bar graph method, same sort of thing, except you might, it helps you keep in mind that the same amount of energy is in the initial and final bar graphs. Okay, so bar graphs are probably a little more physically accurate as to what's happening, but again, the checkbox system can speed things up a little bit, perhaps. So finishing this up, we have the gravitational energy of the girl at the top. Initially is going to equal her kinetic energy at the end, and that's why the energy is transforming. It's changing types of energy, but it's not disappearing. Okay, it's just changing forms. And so mgy initial plus 1, it has to be equal to 1/2 mv final. We see that the mass cancels. That's always nice when that happens. And so her final speed here is going to be 2g, or final speed squared is going to be 2gy initial. The final speed is going to be the square root of that. And of course, since we're talking about speed, we only end up with the positive square root for our answer. V final is going to be 13 meters per second. Okay, so note that this is the same speed the child would reach if she fell 8.5 meters vertically. If she had jumped off the top of the slide, for example, and fallen 8.5 meters, she would hit the ground at 13 meters per second. So, going down the slide, the higher the slide, of course, the faster she'll go. But of course, what we're ignoring here is friction. Okay, if she jumped off the slide at that height, that would be very dangerous, obviously, because she would end up moving at, well, we know that 56 miles per hour is 25 meters per second, so she's moving at a very high rate of speed, certainly going to be seriously injured, probably have a broken bone or something at least if she landed on the ground. Sliding down the slide, her speed increases gradually. We know we lose some energy in friction, and so it ends up being just a fun splash in the water if it's designed right. All right, let's look at another example. Here's another problem from the book, Mathematical. It says we have a 2-kilogram package of tamales sliding along a floor with a speed of v sub 1, it looks like, of 4 meters per second. It then runs into and compresses a spring until the package momentarily stops. Its path to the initially relaxed spring is frictionless, but as it compresses the spring, a kinetic frictional force from the floor of magnitude 15 newtons acts on the package. If K is 10,000 newtons per meter, by what distance d is the spring compressed when the package stops? Okay, so now we're getting pretty serious with this. We've got, again, numbers involved. We're going to solve for a numerical answer for a distance d that the spring compresses before the tamale stop. But we've also got a situation here where we're going to have some friction that's going to generate some heat. We've got a spring involved, we've got kinetic energy, so this is a little different than some of the other ones we've done. So let's go ahead and try this out. Again, looking at things in terms of where the energy is at the beginning and where it ends up at the end. At the beginning of the problem, we see that all the energy is kinetic. The spring is not compressed, so there's no energy stored in the spring initially. If we assume the y equals 0 level is the height at which the tamales are sliding, then we can say there's no gravitational energy. There's no friction or there's no heat added to the problem at the beginning. There may be some heat generated at the end, and indeed there will be, and there's no forces coming from outside our system. So at the end of the problem, the tamales slide over here, they compress the spring, all right, they compress the spring here some distance d, and they do stop. So the kinetic energy at the end is 0. We're still at a height of 0, so there's no gravitational energy. But now the spring is compressed a little, so we will have some spring energy, and so there should be a bar there. And we also know because we have some friction, there should be some thermal energy generated. Okay, so there should be a bar there. Now, what height these two bars should be with respect to each other, no one really knows until we do the calculations. So it's okay if you have different size bars there than I do. It's just the idea here is that this bar plus this bar's height would add up to this bar's height. Again, no work coming from outside the system. So again, if this had, what was that, 1, 2, 3, 4, 5, 6 units of energy over here, that means if I add up this bar, 1, 2, 3, 4, and this one, 1, 2, I should still end up with 6 units of energy at the end of the problem. That's the idea. Okay, so what we do then, construct our energy equation. The initial bar graph equals the final bar graph. So we have a kinetic energy initially over here equals the energy stored in the spring plus the heat generated. Okay, that's kind of how we get our energy equation. Now, once we have that energy equation, it becomes a matter of just carefully plugging in the right values. The mass of the tamales was 2 kilograms, so that goes in for M. The initial speed was 4 meters per second. That's a standard unit, so that can go in for V initial. The K value was given to us as 10,000 newtons per meter. That is standard unit, so that can go in. All right, we're solving for D. We'll leave that as an unknown. Now, our average friction, they actually told us here. Usually for friction, kinetic friction, of course, we have to take mu sub K times the normal force, right? But we didn't have to do that here. Instead of them giving us a mu sub K value and making us, determine F sub n and solving for our own kinetic friction force, they just said, hey, let's assume that the friction force is a steady sliding force of 15 newtons acting, against the motion of the tamales. But remember, over here, what we're doing is we're generating heat. So that's kind of a positive. In other words, the friction here is not taking energy away from the left side of the equation, but we're basically adding heat in at the right side of the equation. So here, this is going to be a positive amount of heat generated, and so we want a positive number there. And so we're taking just the size of the average friction force times the distance that the tamales slide while that friction acts, which is the same as that distance d, that the spring's going to be compressed. Okay, so now we have one equation with one unknown d, but it does turn out to be a quadratic equation. And so at this point, we've got to pull out our, unless we can factor it, or we want to do it some other way, we'll pull out our quadratic formula, and we'll go ahead and solve it. Again, I'm not going to take up the time in our class today or in this lecture to refresh that, to go over that again. You should be very comfortable using the quadratic formula to solve a quadratic equation. You have your constants a, b, and c, and you just use that equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. And if you do that properly, you get about 0.055 meters, which if you want to put into centimeters, you could convert that. That's a little nicer number to give as an answer, 5.5 centimeters. Okay, so only about 5.5 centimeters of compression on the spring to stop this package of tamales. Okay, so this part turns out to be more important probably as you go forward into upper level physics and engineering courses that you might encounter. This idea is that they're associated with every potential energy field, for example, is a force. And there's a nice relationship between these, and it's shown in this yellow box, yellow highlighted box here. It says that the function, the force associated along the x dimension, okay, the force as a function of x and how it might vary, is equal to the negative derivative of the potential energy with respect to x, the derivative of the potential energy with respect to x. Yeah, so f of x is equal to minus du of x dx. So in other words, the force is equal to negative du dx. Okay, they're both functions of x along each part of the dimension. Okay, so what this means is if I have a potential energy for an object and it's varying, if I know the potential energy of my object is varying as shown here in this graph, okay, as I go across, at each position x, I know what its value of its potential energy is. I could construct a graph that that kind of shows me how the potential energy of the object is varying across the x-axis. So, for example, this would be maybe similar to the roller coaster problem that we were looking at, the skater, right? The little animation I ran. So, obviously, if we're talking about gravitational energy, the skater has a lot of energy there. Then they have a very little amount of gravitational energy or potential energy. They have more here, less here, and then a little more up here. So, maybe this is actually, like a hill, okay, if we were talking about gravitational energy. Now, if I take the negative derivative of u of x with respect to x, what does the derivative give us? It gives us the slope, right? So the derivative of, du dx would just be the slope of this graph. And so here we'd have a kind of a steep negative slope, right, for this part of the graph. But keep in mind that we have the minus sign here, right? We have the minus sign, which means that du dx here, even though it's negative, have a negative slope, it's actually going to be a positive value as a force. Okay, and so when you look at the graph over here, what we see happening is, if I was the skater, it would feel as though there's there will be a positive force pushing on me as I go down this hill, right? And then as I come down to here, the force kind of disappears at x2, and then as I come up this hill, right, I'd have a positive slope in du dx here, but again, there's this minus sign here. So we'd have a negative force, which would do what? Slow me down. And so that's why I see the force coming down here negative, right? And so again, what you see happening here is when we take the negative derivative of the potential energy with respect to a dimension like x, then what we get is a graph of the force along that dimension. Okay, and that's a nice handy thing to know, and does come in handy and has a lot of good application, especially as you go up into your higher levels of science and engineering. And again, we already talked about this idea of power. I just want to revisit it quickly because when we talked about power previously, I think we talked about it as the time rate at which we did work, dW, dt, something of that sort. Keep in mind that it could be any type of energy converting, and there's a power associated with that. So it doesn't necessarily just have to be work. Any type of energy that's converting from one form to another, there's a power involved with that. And the instantaneous power, of course, would be dE dt. They're basically writing this equation, up here, saying that if you know the change in energy, how much energy changes types or whatever in a period of time delta t, then the average power during that time is delta E over delta t. Of course, if we use the calculus version of that equation, we get our instantaneous power. And it's just important that you realize that power isn't just for when work's done. It can happen when energy changes forms as well. There's a power associated with that. Okay, now we get to the machines, the simple machines part of this lecture, and we want to talk about simple machines for just a few minutes because it's probably one of the most practical applications of what you've been learning about energy as there can be, and it'll be useful to you all your life. When I took Physics 211, this was kind of brushed over pretty quickly. I guess the professor figured we'd figure it out on our own, or we already knew it, or whatever. But what I found was that this is the kind of stuff that even if your career doesn't go the way you want here, and you end up dropping out of college or don't get your degree or whatever, or you decide to change majors entirely and become a poet, for example, this material right here on simple machines will be of value to you your entire life. Okay, if you remember it, and it's not that hard an idea. Okay, so first of all, what is a machine? A machine is a device that multiplies force and or changes the direction of a force. That's really all it has to do. If it changes the direction of a force or multiplies a force, makes it bigger or smaller, then it's a simple machine. Okay, and probably the first simple machine that to talk about here is the lever. And the lever is a simple machine, and the way it works, we're going to do a laboratory where we do some balancing on a meter stick, one of our labs this semester. But when we look at this, the way a lever works is it's basically let's say a stick or some kind of rigid arm that we prop over a support, which is called the fulcrum. Okay, this thing down here that the meter stick or stick, whatever this is balancing on at this point right here. That's called the fulcrum of the lever. And when we use a lever, the idea is we push down on one side, right, and we get a force out on the other side. Now, if you have the fulcrum right at the middle of this, if you just had the stick like this and you had the fulcrum right at the middle, then of course whatever force you push down with, that's the force you're going to get out. Okay, there's no multiplying a force. You're changing the direction of the force, so even a lever used like this is a simple machine. But if we want to get force multiplication, then we're going to learn as we go further into the course that we can get more force out than we put in as long as this input side of the lever is longer than the output side. Okay, so if I wanted to lift a big heavy rock that's stuck in my garden or something, and I want to pry it, I could take a 2x4 or something, get it underneath the rock, put a small rock down here for the fulcrum, and then push down on the end of this 2x4. And as long as this distance is big, right, as long as that input distance is big, I'm going to get more force out than I put in. More force out than I put in. And at first that seems like a violation of the conservation of energy. Right? You're saying, well, how can I get more force out than I put in? But what's happening here, we use a smaller force over a larger distance. So when you think about work, right, the work done and the work output is exactly the same. There's no making of energy. If I use a smaller force but a bigger output distance or input distance, then I can get a bigger force on the output side over a smaller output distance. So if you look at this, and think about it, well, actually, they show it to you in the diagram. I just don't know how well you can see it or you recognize it. The distance that this force was pushed on the input side, notice how long that is. I mean, I pushed the input side of the lever that far. Now, on the output side, I've only got the rock moving or whatever I'm trying to lift up. I only have it move that far. So this distance over here is much smaller than the distance over here that I pushed the lever down. It turns out that the relationship is very similar between the lengths of the moment arm here, as they call it, okay, and the output moment arm. These lengths are very similar. The ratios are the same as the lengths of these little d's here. So it turns out I'm not making energy, but here's the equation that dictates what's happening. So if I want to get a big force out, right, then I want a big distance for the moment arm, and I want to move the input moment arm over a large distance. So the bottom line is simple machines are spreading out the work. All right, listen carefully to this. This is important. Simple machines, the basic idea of all of them is that you want to take the work and spread it out over a longer distance. When you spread the work out over a longer distance, you can use less force and it seems easier. In the long run, you've done the same amount of energy doing it this way, prying the rock out of the garden, as you would have done if you just used a humongous force over a little distance. All right, I could bend over, try to lift up the big heavy rock and lift it up this short little distance and probably hurt my back. Or I could lift it up that same distance by using a smaller force, pushing downward and doing it over a bigger distance. So by spreading the work out over a longer distance, I end up making the work easier for myself, or at least it seems that way. So here we see kind of a cleaned up version of that. The force input times the distance I move it over is equal to the force output times the smaller distance that I move it over. So because these distances are so much different, I end up with a similar enlarging of the force that I'm outputting. Okay. Now again, we can't make energy, so there's no way I can get more energy out than I put in. And as a matter of fact, because there's probably some friction, right? There's, nothing is perfect. There's probably a little bit of friction in that pivot. Plus, I've got the weight here, the lever arm over here that I'm kind of lifting up with my load. And so, I'm not making energy. If anything, I'm actually putting more energy in. I'm doing more work than I'm actually getting out. But it will seem like a much easier process to me because of this force multiplication. So that's the idea of all these simple machines. We're going to talk about a few more, but that's kind of the theme of all of them. Increase the distance over which you do the work so you can use a smaller force. Pulleys are simple machines. Pulleys are simple machines, but you have to hook them up the right way. Okay, when I was a student, before I really understood all this, I thought you used a pulley kind of like what this girl's doing here. You hang the pulley from the ceiling, you throw a rope up over it, you attach your load onto it, and then you pull, right? And I was thinking, okay, yeah, that'll make it easier. Well, it turns out, if you look at it, if this box has a weight W, then I have to pull up with a force in the rope W. That's a continuous rope. It's coming over to here. I still have to put a force W in. So my force has changed directions. That's true, right? The way she's using it in this top example, she's changing the direction of the force, but there is no mechanical advantage here at all, other than the fact she's maybe pulling down and can use some of her body weight, but really she has to pull on the rope exactly as hard as the box, as heavy as the box is. So if this was a 100-pound box, if she was lifting a 100-pound box, she'd have to be pulling with 100 pounds of force in her rope there. On the other hand, if you look at the bottom diagram, if you take the pulley and you hook it up, you hook the pulley up to the, oops, let me get the yellow marker, that's what I wanted. If you take the pulley and you hook it up to the load, the thing you want to lift, okay, take the rope, tie it up here to the ceiling or to some rigid object up here, and then run the rope down under the pulley and she lifts up. Now something very interesting happens, because when we look at this, we really have changed this situation so that we have a support force here, right? That rope's helping to support the pulley, but her side is also helping to support the pulley. Okay, so we actually end up only having like one downward force, right? The weight of the load and the pulley, and we have two upward forces. We have some support force here, and we've got some support force here that she's pulling up with. We actually have two ropes now pulling up on the load. And guess what happens? The tension in a continuous rope is the same, remember? So what we end up happening here is we end up getting a mechanical advantage of 2 to 1, all right? 2 to 1. In other words, if this box had a weight of 100, oops, yeah, I'm messing up my colors here, 100 pounds in this case, the rope tension would be 50 pounds. And all she'd have to be pulling with over here is 50 pounds. So she would be lifting a 100-pound box using a 50-pound force. Okay, and again, how do you lift 100 pounds with only 50 pounds? Well, you trade off distance. Okay, so now if you think about it, you actually think about the length of this rope and what's happening here. As she pulls this rope and shortens this rope and lifts the object up, if she pulls 1 meter, right, 1 meter here, that's the rope shortening by 1 meter. But the rope comes up under the pulley, and so the load only gets lifted a half a meter. So for every meter she pulls the rope up, the load's only going to get lifted a half a meter. Right? We lose a half a meter from each side of this. We'd lose a half a meter over here and a half a meter over here on this side, and that's our meter of distance of the rope. So what you're doing, again, with the pulley, if you hook it up the right way, is you're increasing the number of ropes pulling up on the load, right? You could add extra pulley wheels in here. You could add, extra loops in here. But however many ropes you're pulling up with, that's going to be your mechanical advantage, okay, at least ideally. Okay, and what you're going to trade off is distance. Okay, the more ropes you have going underneath pulleys, she may pull this, if she had 10 ropes, she'd have to pull the rope 10 meters to get the package to come up 1 meter. Okay, you're trading off distance for force. You're saying I'd rather use a smaller force over a longer distance because that seems easier to me than using a huge force over a short distance. So again, one more time, because this is the real theme for it. So you can almost use this rule the rest of your life, and it will help you figure out clever ways to save yourself some, make jobs seem easier around your house. If we want to use a smaller, power output, or if we use smaller power output, the job seems easier to us. We want to use smaller power coming out of our bodies. And in general, the way to do that is to use longer distance and a greater amount of time. So we want to spread the work out over a longer period of time, because when our body puts out a lower power, it seems easier. For example, walking up 6 flights of stairs would burn the same number of food calories, the same amount of energy, right, as running up 6 flights of stairs. Okay? The difference is if you run up 6 flights of stairs, you're done with that job quicker, right? And so it seems harder to run up 6 flights of stairs. If we ran up 6 flights of stairs, right, ran to the 6th floor of a building, we'd find ourselves huffing and puffing and breathing hard and bending over and so forth by the time we get to the 6th floor. Okay, whereas if we walk up to the 6th floor, we're going to get up there and we're not going to be huffing and puffing or perspiring as much and so forth, because it seemed easier to walk up the flight of stairs. But at the end of the day, we've burned the same number of food calories. The difference is the higher power situation, the work being done over a shorter period of time meant we had a higher power output. And the bigger the power output, the harder it seems. Okay, so we want to decrease our power output because high power situations seem hard to us. Okay, a ramp is a simple machine. You may be thinking, wait, a ramp doesn't even have any moving parts. And that's true, but it is a simple machine, and here's why. They show in this diagram a girl sliding a block of ice up a ramp, and they show a boy lifting the block of ice up the same height. Okay, you could say, well, who slides blocks of ice anymore? Well, that's fine. You could just as easily say we'll use a bag of cement, a big heavy bag of cement down here, and we'll put it on a cart, okay, with wheels. All right. So which would seem easier, lifting up the bag of cement like this? I mean, if I have a bag of cement I have to lift up and I do it, I can use a big force out. I could put a big force out of my body, and I could use a little distance and lift it up like 1 meter high, but I'm probably, because of this big force, going to hurt myself, or it's going to seem really hard for me to do. On the other hand, if I put it on a cart over here and then I push it up the ramp, right? I push it up this ramp like the girls seen doing. I push it up a long ramp. I've ultimately, at the end of the day, lifted it at the same height, right? I've lifted it up to the same height as I did over here, but I did it over a longer distance, and so it's going to seem easier. Okay, it's going to seem easier. As a matter of fact, if you have a big, long, gradual ramp, right? The longer the ramp is, and the more gradual it goes up, the more mechanical advantage you'll get. In other words, pushing a cart, pushing a little wagon here with a bag of cement on it up a very shallow ramp is much easier, right? It's much easier than lifting it straight up here. And so what will be the mechanical advantage you get? Well, it's just simple. It's like the ratio of the lengths here, right? So if the length of this hypotenuse is d and the height that I've lifted it up is little d, the mechanical advantage I'm going to get is capital D over little d. So if the ramp is 10 times longer going up than it is going upward, I get a 10-to-1 mechanical advantage. It's just that simple. Pretty cool stuff, huh? And this relates back to something I learned as a kid, and some of you may have learned already in your lives, and that is I grew up in western PA where there's a lot of hills, a lot more hills even than there are around here. And so when we rode our bicycles, when I was a kid, they're 10-speed bicycles. Most people didn't have those. We had just regular bicycles. And to ride a bicycle up a hill, when you rode a bicycle straight up a hill like that, the hills could be very steep, and usually halfway up the hill, it gets too hard, and you just get off your bicycle and walk it up the hill. Well, my brother taught me when I was a kid. Sometimes I would ride my bicycle back from baseball practice, and I'd be holding a baseball bat and a baseball glove hooked over my handlebars of my bike. And I didn't want to have to stop and get off and push the bike. And he told me, well, if you weave your way up the hill, you'll be able to climb the hill on your bicycle without having to stop and get off. And I didn't really think much about that as a kid. I mean, I knew it worked. He taught me that, and I tried it, and I was like, oh, son of a gun, that idea works. But now you can see how this relates back to the ramp, right? Because if I were to go across a hill, just going straight across like this, I don't even change height at all, right? I mean, in other words, if you look at this wedge here, that hopefully you see the three-dimensional aspect of that. If I go across the hill, right, without going up or down, I don't even change height at all doing that. And so the idea here is that by taking just a slight curve, angle like that, I've reduced the steepness of the hill along these sections where I curve. And then all I have to do is have enough, momentum in my bicycle to kind of carry around that little curve connecting these, okay? And then I can get all the way up the hill. So basically, I've lengthened the hill by weaving back and forth up the hill. I've lengthened the hill. I could lengthen it even further by doing this, right? I mean, if I weaved even more, again, I could get these back and forth routes. I'm climbing the hill little at a time, little at a time, little at a time, and it'll seem so much easier than trying to ride my bike straight up the hill. So again, there's another application of it. Also, a screw. While I'm thinking about it, if you think of a screw, this is a class that's, I know many of you are, engineers and so forth. And so if you think of a screw has threads on it, and the threads on the screw, they kind of come up around, and it's almost like a ramp spiraling around on the screw, right? That's what it is. You get this little angle thing that sticks out on the edge of the screw. It kind of wraps around and comes up the central shaft of the screw. And so when you turn the screw, you're getting a lot of, if you've ever put a screw through two pieces of wood that have some glue between them, when you screw the boards together tightly, you'll be amazed at how much glue squeezes out. Sometimes you'll feel like there's more glue coming out than you put in there because you're getting tremendous leverage. You're getting tremendous output force with this screw because it's doing the same thing. It's pulling the two boards together over a fairly short distance, but it's doing the work over a long distance of turning, and so you get an incredible amount of force out in that situation, more than you actually are, with your turning up here, your input force turning the screw, you're going to get a lot more force drawing the two boards together than what you put in up here. This will be a small amount of force compared to the force you're getting out with that leverage there from the screw. So the screw is kind of a spiraled ramp around the center of a spiraled ramp around the center shaft of the screw. That's what a screw is. Now, to finish up for today, I've got 4 different situations, so I've got a left and a right situation for 4 different scenarios, okay? And what I want you to do, just to make sure that this whole little section on simple machines makes sense to you and that you've got the idea, I want you to take a look at these situations. We've got a ramp on the left and a ramp on the right with the same object being rolled up both ramps, all right? And then we have a wheel and an axle, kind of like a crank, where one has they both are lifting the same weight object. And then we have a couple levers being used in different ways, different lengths. And then we have down at the bottom some pulleys. Now, if you can't see this real well, you probably can't because of the resolution. There's actually 4 strings here pulling up. There's 2 here, and then there's 2 more over there. Okay, so that actually has 4. This one only has 2 over here. This one only has this one and this one. Okay, this pulley arrangement has 1 here, 1 here. So this has like a double set of wheels. Okay, the pulleys here have like 2 wheels each. Okay, so hopefully that makes sense. Now, what I want you to do is just pause the video, and I want you to circle or indicate on your page somehow which situation you think has a greater mechanical advantage, which one will seem easier for you to do. So pause your video and then continue to see if you got the right answers. Okay, hopefully you got the answers here. Of course, this ramp is a much longer ramp, lifts the object up over the same height, but does it over a longer distance, so this one will be easier. This crank, you're cranking your input hand over this distance while you lift this would be like a bucket in a well, the old-fashioned well where you have a bucket of water and you're lifting it up over the shaft here and cranking. In that process, each turn of the crank is going to lift the bucket up a certain distance here. So your output distance is pretty small for each turn, but here you're only turning your hand around that distance. Over here, you're cranking your hand, your input force cranking the rope is over a much longer distance because it's a bigger circle. So these bigger cranks will seem easier, that side's going to seem easier to crank. If you think about those penny machines, they still have them. A lot of them are mechanical or have a machine in there that does it for you, but you still see, in some tourist places, you'll see the machine that has the gears inside and so forth, and you could put in a penny and then crank the crank and smash the penny, and you'll notice that the crank handle on those machines is very large, so that you move your arm a very big distance, which actually gives you, makes it seem easier. It gives you enough force to smash the penny. Over here, bigger input arm over here. If I'm pushing down over here, I've got a bigger ratio of D to D here than I do over here. It's a smaller amount, so this one will seem easier. And then with 4 ropes pulling up, I only have to put in a force of about 1/4 the weight of the box. Over here with 2 ropes pulling up, I'd have to put in a force equal to 1/2 the weight of the box. So this one over here on the left would seem easier. So hopefully this idea of conservation of energy makes sense. You got to continue to practice problems. The more you practice, the easier it gets, the better sense it makes. Contact me outside of class if you have questions. Otherwise, we will see you in class on Friday. Thanks for listening.